I'm Bryce Adelstein Lelbach. I'm a principal architect at NVIDIA, and I've spent the past over a decade now working on programming languages and compilers. And the reason I'm here today is that I've spent a lot of my time working on C++, and I chair the C++ standard library evolution group, which is responsible for designing the C++ standard library. So today I'm going to talk to you about some things that I'm excited about that are on the horizon for C++. So let's first talk a little bit about where we are today. So C++ 20 was the largest release of C++ in over a decade. It delivered 4 major features: modules, coroutines, concepts, and ranges, and dozens of other additions and improvements. It's changed the language in ways that really no other release has, with the addition of things like modules that impact all of our tooling and our build systems. And so it's taken a little bit of time, but now C++ 20 is widely available. Most implementations are shipping most of C++ 20 in production. And we're seeing increasing adoption and more projects and organizations switching over to C++ 20 as their default. Now, the next C++ standard, C++ 23, was completed back in February. This is not as large of a release as C++ 20, but it's one that I'm particularly proud of. And I think there's a lot of exciting things here. To name a few, there's a bunch of enhancements and additions to ranges, sort of completing a lot of the ranges work that we did in C++ 20. We've added a new formatted output facility, something that's near and dear to my heart, MD-span, which was actually the reason that I joined the committee back in 2015. Only took about a decade, but now it's finally shipping in C++ 23. Expected a new error reporting paradigm, standard library modules, and deducing this, and a number of other fixes. Now, in the months leading up to a new release of C++, our focus, both within the committee and within the community, is often on what's going to go into that release and what doesn't make it. And we tend to put longer-term goals on the shelf. But today I want to dust off some of those longer-term goals. Now that we're done with C++ 23 and we can start looking at C++ 26 and beyond, I want to look at what is the things that we're going to be working on for the next decade. So I want to tell you about 3 features that we're working on in the committee, features that I think will revolutionize how we write C++ code. And those features are reflection, pattern matching, and senders. So our exploration today is going to focus on what we can do with these facilities, not so much the specifics of the committee proposals or the merits of different design decisions. This is a talk about possibilities, not details. Assume that all of my code is more or less pseudocode. Much of what I'll show you is going to be tentative and in some places purely speculative. In places where the design is uncertain, I've just chosen the option that made the most sense to me, and I've sort of ignored the alternatives or the discussion. This talk represents my own views. I don't speak for the committee. This is just what I'm excited about and the shape of things that made sense to me and made sense for my slideware. So let's start off with reflection. So reflection is inherently tied to metaprogramming. And I'm going to define metaprogramming as the craft of creating or modifying programs as the product of other programs. So reflective metaprogramming is metaprogramming that incorporates data from the program that's being modified. So there's 3 key components to reflective metaprogramming. First, there's reflection. There's extracting information from the program itself. And then you need some compile time programming facility, which are just tools for manipulating that information. And then finally, you need a mechanism for injection, for inserting new program entities based upon those compile time computations that you did. So let's look at a simple example that uses reflection. So this is a function that takes an enumerator and returns its name as a string. So we're going to use a few new proposed C++ constructs here in this example, and I'm going to walk you through them. So first we have this hat operator, which is called the reify operator. And this takes a C++ entity that could be a function, a struct, an enumerator, a variable, a namespace, and it produces a reflection. Now, what is a reflection? A reflection is a handle to an internal compiler representation of the type. So in this case, of the thing T. So std meta info is the type for reflection objects. It's sort of this opaque handle to any type of reflection. Reflections can be manipulated and transformed just like any C++ object. So here, we're passing the reflection of the enum type T to the function meta members of. So meta members of is this compile time function that takes a meta info and returns a meta info that represents all of the enumerators of T. So one of these meta info objects, it can represent not just the reflection of a single entity, but it can also represent a sequence of entities. In this case, a sequence of the reflections of the members of T. So we can iterate over one of these meta info objects using a range-based for loop. And here we're going to use a new type of range-based for loop that's been called at some points in time an expansion statement. I'm going to just call it template for here. So this is a compile time expanded for loop. For each element, it may be a different type, and essentially it stamps out the body of the for loop for each of those types. And it's completely evaluated at compile time. So in each iteration of this compile time for loop, we want to check if the enum parameter of the function is equal to the value of the current enumerator in this iteration. So to do that, we need to take the reflection that we have, the reflection of the current enumerator, and we need to turn it back into a real entity so that we can compare it to the value that was passed into the function. And we do that with the splice operator. The splice operator takes a reflection value and turns it back into an entity into the entity that it represents. So in this case, it's a reflection of an enumerator value, so splicing it will give us the enumerator in question. So if the parameter is equal to the current enumerator, then we need to return its name. And we can get that name with another function that operates on reflections, meta name of, which just returns a string view of the name of the thing. And then, of course, if we didn't match any of the enumerators, we just give up and return unnamed. Okay, let's look at another slightly more advanced example. So this is an implementation of hash append, which is a hash protocol that incrementally passes input to a hash algorithm. This is useful if you want to hash some type that is a aggregate of other different components, or something that's like a vector that you want to hash everything within the vector. So this hash append function is going to take two arguments. One, a hasher object, which represents the hash algorithm that you're passing this input to, and then the object that is being hashed. So what we're going to do inside of our implementation of hash append here is we're going to reflect on the object that we're hashing, and we're going to use the members of function to get all of its members. Now, the members of function takes an optional parameter here which filters for certain kinds of members. In this case, we only want the non-static data members. And so we're going to say that that's all that we want here. And so next, we're going to do a template for over all of those data members. And then we'll use the splice operator to access that data member. And then we'll recursively call hash append on the member. And not shown on the screen here, but for things like built-in types or stood vector, you would have a different overload of hash append that does the right thing. But for just your generic user-defined type, this would split it up into its constituent parts and call through to whatever other overloads or specializations exist. Okay, everybody following so far? Because we're about to get to the slightly more complex examples. All right. We can even inject a class scope too, allowing us to build powerful wrappers. So here we've got a traced class, and that's going to be a class that wraps another type and adds a print call before invoking each of the underlying methods. So you take some type that you wrote and you give it to traced, and traced goes through and takes every method of your type and generates a method in traced with the same name that takes the same parameters, but will print that it's calling that method before it forwards the call to the method in your underlying type. So traced has a data member of the wrapped object. We're going to call it payload here. And we're going to use a template for at class scope to generate a member for each member function of the wrapped type. So this is a little bit novel, but if you think about it, you can't normally use a for loop at class scope because it doesn't make any sense. But if this is a compile time for loop, well, why couldn't we? Okay, so inside the body of this class scope template for, we need to inject for each member function of the underlying object, we need to inject our own member function. We need to generate a new member function. So first we need to inject the signature. So we need to get the protection of the underlying member function. We need to get the attributes and the return type of whatever method we're wrapping. So that's pretty straightforward. And then we need to insert the name of it. And this is where we've got something new here. And to name this method, we're going to use a different type of splice operator. We can't use the regular splice operator here because the regular splice operator would inject the method of the underlying type. But what we want really is to inject an identifier here. So think of the regular splice operator as injecting something akin to a pointer to member function. We can only really use that on the underlying type, not on the wrapping type. And so that's why we have the identifier splice, which uses the hash instead of the colons. And the identifier splice operates at the lexical level, and it inserts a name, the name of the thing that you're reflecting upon. So next, we need to generate the parameters for the method that we're inserting. And so here, we're going to use another new thing, splicing pack expansion. So by adding, as I mentioned before, these meta info objects, these reflections, can potentially be a collection of things, like the collection of members or a collection of parameters in this case. And so it's convenient for us in some cases to be able to treat one of these as if it was a parameter pack. And you can do that by adding triple dots before a splice, which will cause it to expand into a parameter pack-like thing, which can be unpacked with a trailing sequence of triple dots, as shown here. Now, in this case here, we actually need two different parameter packs. We need both the types of each of the parameters from the underlying method, and then we need to insert the names of each one of those. And we're going to use the regular splice for the types, and we're going to use the identifier splice for the names. I know there's a lot of dots here. Hopefully that made sense to all of us. Unfortunately, there may be more dots coming. So then, now we're finishing up the signature here. We're going to inject the qualifiers of the underlying method. So finally, we need to generate the body of the wrapping method. So first, we're going to print out the name of the method that we're calling. And of course, we could do something more complex here. We could print out the name and the signature. We could print out all the parameters because we have all of that information. So next, we need to generate the call to the underlying method on the underlying object that we've stored. So note that here we're going to use the regular splice operator, not the identifier splice operator, because we're operating on an object of the type that we're reflecting on. We could use the identifier splice operator here, but there's really no need to. So then we're going to forward all the parameters. And then we need to inject the names of the parameters that we're going to pass to this call. And again, we're going to use splice pack expansion. So here, we're going to use the identifier splice, and that's again because we're not referring to the parameters of the underlying method. We're in the wrapping method, and we want to refer to the parameters of that wrapping method, which happen to have the same name as the names of the parameters of the underlying method. And so we'll use the identifier splice here to name all of them. And with that, we're done. We have our traced class. So reflection can also be a powerful tool for automating data layout transformation and optimizations. One common transformation that can have huge performance impacts is switching between an array of structs where data is stored as a single sequence of multi-component elements and structive arrays where data is stored as one sequence for each separate component. So switching between these two usually requires structural code changes. So as you can see on the left here, we have array of structs, and on the right, we have structive arrays. And we've had to change a little bit what our struct looks like and how we construct one of these and how we iterate over one of these. So an array of structs is often more intuitive because a single element consists of a single type. It keeps things that are logically together. But structive arrays usually offers better memory access patterns, which can be critical when parallelizing or vectorizing. So consider this code, which implies an operation to just the red channel of a sequence of colors. So this will have a strided memory access pattern, and in some cases, it may have alignment issues, which would inhibit vectorization. So we can use reflection to write a wrapping type that automates transforming from array of structs to structive arrays. So first, we need to get the non-static data members of the type that we're wrapping. Then we inject a vector for each data member of the underlying type. And we're going to do this again with the pack expansion splice operator here. We could also use a class scope template for. So this constructor here will initialize this wrapper from a range of the underlying struct, so from array of struct data. So we use a template for in the body of this constructor to iterate over each of the component vectors. And then for each component vector, we resize it. And then we copy from the range of array of structs data. And so we're going to iterate through that range n times for each of the components. But that's going to be fine because it's often going to be more efficient to copy these component-wise, and we're going to build a more efficient data structure to work with. So we can make our wrapping structive arrays a range of tuples of references to the components so that it can be iterated over as if it was an array of structs type. So here, I've shown how you might write an indexing operator where we use the identifier pack splice operator to get a pack of the elements from of the element at a particular index in each of the component vectors. And then we can use tie to return a tuple of references to those elements. So you can use this same approach to create actual iterators where the iterator's value type will be a tuple of references. In the interest of brevity, we're not going to look at how we'd do that. It would be more code than would fit on the slide. But I think that this shows you the general idea here, that this SOA thing is intended to be a range whose element type is a tuple of references. And that's useful because then you can take this code here, which does a range-based for loop that decomposes my struct into its three components and has a poor memory access pattern. And just by changing from vector to SOA, we've switched the code from array of structs to struct of arrays. And this changes our memory access pattern for our single channel operation from strided access to contiguous access, which is more cache efficient and easier to vectorize and parallelize. So I think that reflection will fundamentally change how we will write C++ code. It's going to help us solve problems that today often require boilerplate, macros, or external code generation. Things like serialization, protocol or language bindings, instrumentation, logging, debugging, data layout transformations like SOA to AOS, even things like automatically generating SIMD types from your scalar types. It's going to change how we build and design libraries and how we evolve the standard library and the language itself. So now let's move on to pattern matching. C++ today has two types of selection statements. Switch operates on a single integral value, which is often too limited. You can't use them with string literals or objects. If statements, on the other hand, operate on arbitrary Boolean expressions. They're powerful and can express almost anything, but they're often too complex and verbose. What we need is something that's in between the two, a powerful but concise way to select and decompose objects. And that's what we get with inspect, a proposed new selection statement for C++. Inspect matches values against patterns and binds variables when matches are successful. Inspect is an expression, not a statement. An inspect expression takes a parameter, the object to select against, and a series of patterns. There's a variety of different patterns available. I'll highlight a handful of them today. So each pattern is followed by a statement, which is taken if the pattern matches. Inspect stops at the first match, not at the best match. So the first match in lexical program order. So constant patterns match if the object is equal to the constant. And the wildcard pattern will match anything. And the wildcard here is double underscore or single underscore or some other character depending on the particular week and the particular committee member you ask. So constant patterns aren't limited to integrals or enums. They can be strings or any arbitrary object. So let's look at an example. This is Fibonacci written with inspect. So here we use the identifier pattern as the last pattern in this inspect, which will bind the value to a name. Now, pattern guards can be used to perform arbitrary tests for a match. In this case, we want to make sure that the integer is not too large, otherwise we'd overflow. Now, since C++ 17, we've been able to destructure tuple-like objects. We can do that in inspect too with compound patterns. Alternative patterns can match different types, invariant or any-like objects, or polymorphic objects. They can also be useful when working with dependent types in a template. Now, extractor patterns allow us to completely customize matching and decomposition by implementing our own extractor protocols. An extractor is just an object that has either an extract or try-extract method. When an extractor pattern is used, this method is called with the value under inspection, and then the result of that call is matched against the child pattern. So for example, in the first pattern in this inspect, phone number.try-extract will be called, and if it returns a value, that value will be matched against the compound pattern here. Okay, we ready for a more complex example? Prepare yourselves. Okay, so this is an example of how you can use both reflection and pattern matching to generate some JSON from C++ types. So this save JSON function will take some arbitrary object, and we're gonna just write it out to a string because it's less code than doing the proper thing and having it output to an iterator. So, sorry, slideware. Now, the first thing we need to do, we need to get all of the non-static data members, which we do by reflecting over T, and then using members of with the is non-static data member filter, just like we did in hash append. So then we've got a template for that's going to iterate over all of the members. This time we're doing something a little more clever. We are doing an index-based for loop here. And the reason for that is that we need to know where we need to put the commas. So we need to know when we're at the end so that we don't put a trailing comma. Now, fortunately, the idea is that these meta info objects will be random access so that you can use the indexing operator with them and you can ask them what their size is. So our template for loop here will be not over the members themselves, but will be over indices. And we'll use views iota to get those indices. So then when we're in the body of this for loop, we're going to get the reflection for whichever member we are currently on. And then we're going to start off by outputting the name of that member in JSON, and then a colon. That'll be like the key part of the key value in the JSON. And we're going to do an inspect that will look at the value of that member and the type of that member and determine what to do. So if it's a Boolean, we just output true or false. If it's something that satisfies a numeric concept, then we'll just call std format on it. So note that in the first one there, we had a pattern that matched a type, a concrete type, a Boolean. In the second one here, it's a pattern that matches a concept. And then here in this third one, we've got, this is an alternative pattern that matches a concept, pointer. And then it's combined with a constant pattern. So this is matching a pointer that is a null, specifically. And if it's a pointer that's null, then we're just going to output null. Now, if it's a pointer that's non-null, in the interest of brevity, we're just going to print out the address of the pointer. Now, if it's a string view or something that is convertible to a string view, we're going to print it out, quoted in double quotes. Now, here's where things get a little bit interesting. What if it's a range? Well, if it's a range, we're going to take advantage of the support for formatting ranges of things, which just happens to output things in the correct format for JSON, which is square brackets that are with each element comma separated. We just have to make sure that each one of the elements is correct JSON. And so we'll take the range and we'll apply a transform view adapter to it. And that transform view adapter will just apply this save JSON function recursively. And then finally, if it didn't match any of those things, we just assume that it's an object. And so we call save JSON and just print out whatever that gives us. Then after that for loop, we had the closing brace from the one that we opened just before the for loop. And then we have this little bit of logic that figures out whether we need to insert a comma. And then we return the string that we've generated. And that is a very simple example of how you might generate JSON, probably fairly buggy. Send me emails. But I think it illustrates the power of these facilities. So inspect gives us a powerful new way to select and decompose objects. It makes working with tuple-like and variant-like objects far more natural in C++. And I think it's going to really revolutionize how we write C++. It'll make expressing conditional logic a lot more simpler and a lot more natural. Finally, let's talk about asynchrony and parallelism in C++. So today, C++ has no standard model for asynchrony and no standard way to express where things should execute. And that's why we're introducing senders, a model for asynchronous execution in C++. Now, there are three key concepts in the sender model. First, there's schedulers. Schedulers are lightweight, non-owning handles to execution contexts. Schedulers produce senders. Now, senders represent asynchronous work that will eventually send a signal. A signal is either success and a set of values produced by the work, failure and an error produced by the failure, or cancellation. Senders can be composed together with sender algorithms to form task graphs. Finally, we have receivers. Receivers are connected to senders and process the asynchronous signal that is sent by senders. But today we're mostly going to talk about senders and schedulers. Receivers are sort of a behind-the-scenes detail. You only really need to think about them or know anything about them if you're writing your own senders, not if you're using senders and just writing asynchronous code. So let's look at a simple example. So first, we need to get a scheduler from somewhere. Now, that scheduler could be something that's attached to a thread pool, a tasking system, a GPU driver, etc. To start a chain of work on that scheduler, we call schedule, which returns a sender. That sender will complete on the execution context associated with the scheduler. Next, we use a sender algorithm, then, to compose work onto the sender that we got from the scheduler. This work will be performed on that same execution context. The sender algorithm will return a new sender, which we can use to add more work onto the chain. And there's a variety of other primitives, similar to then, that we can use to build more complex workflows, like forks and joins. Finally, we wait until that chain of work has completed using sync wait, which will return the value sent by the final sender in the chain. So this pipe syntax gives us a clean way to compose chains of senders in the order that they will be evaluated. Just as how we have a pipe syntax for range adapters that gives us a clear syntax that has the adapters appear in the lexical order that they will be evaluated. So we've developed at NVIDIA a prototype of senders called StudExec. It's open source. You can go find it on GitHub. And it supports CPU schedulers, GPU schedulers, and distributed schedulers. We've got a couple different example applications there. This one is a simple electromagnetic wave simulation that solves Maxwell's equations on a uniform grid. So this is the entire solver loop, which is expressed as a graph of senders. This repeat construct here is a sender adapter that sort of models a for loop. It invokes the underlying sender a certain number of times or until a certain condition is met. So this code can be run with a variety of different schedulers. By just changing one line of code, the kind of scheduler that we pass to the solver, we can go from running inline on a single CPU thread to running in parallel on the CPU using OpenMP or a thread pool, to running on a single GPU, to running on multiple GPUs within a single node, up to multiple nodes, scaling up to thousands of GPUs. So we've ported a simulation from the Palabos fluid dynamics framework to senders. This simulation models carbon sequestration techniques. The porous structure that you see here is sandstone saturated in salt water. The red bubbles are liquid CO2, which is injected at the bottom and travels through the sandstone because of buoyancy forces. Using a distributed GPU scheduler, we've run this application on up to 512 GPUs. With C++ senders, you can take this code and by just changing one line, you can go from running on a single CPU on your laptop to running on an entire cluster of GPUs. All right, let's look at some more examples. So this is an example of a simple asynchronous network read, which is going to do two different parts. First, we're going to read how large the buffer is that we are going to be sent, and then we're going to read a buffer of that size. So this is relying on the existence of some underlying async read function, which I'm not going to show here. I just want to show the pattern of the I/O. So first, we have this dynamic buffer type here, which is just a unique pointer to a unique pointer array of bytes, and then the size that we're going to read. So our async read array function will take a handle, which is, it could be the socket, it could be, some other handle, depending on whatever network protocol you're using. And it's going to return you a sender that sends a dynamic buffer. So inside of this function, first thing we're going to do is use the just sender factory. So just takes a just regular C++ value and produces a sender that sends that value. So it's a way to take something from the synchronous world, some immediately available value, and turn it into a sender to introduce some data at the start of your asynchronous pipeline. So next we're going to use let value. And let value is a sender adapter that's somewhat similar to then, which I showed earlier, which is it's going to take a function and it will invoke that function when it is sent something by the previous sender in the chain. The reason that we're using let value in this particular example is for lifetime. We want to keep the buffer alive for as long as we need it across multiple different asynchronous operations. And then we want it to be destroyed at the appropriate time. So inside of let value needs to return a sender which will be appended onto the chain, unlike then, which just invokes work. So we need to build another sender chain inside of this let value, and we'll start off again using just. And this time we want to inject a span to the buffer. In this case, it's just a span of one element, which we're going to use to, this is inserting a span to the size element of the buffer, which is the first thing that we're going to fill. So the network protocol here is that on the sending side, we're expecting them to send us a size t that has the number of bytes that are in the buffer, and we're going to read that first, and then we'll know how many bytes we need to read from the buffer. So then we do an async read on our handle, and then we attach a then, which will be run once that async read is completed. And so inside of this then, we will have the size of the buffer. First thing we do is we make sure that the read was actually successful, that we read the number of bytes that we expected. In this case, it's the size of a size t, the size method of the size member of the dynamic buffer. And so if we've been successful, then we need to allocate storage for the data that we're about to read, now that we know how large it is. And so we'll do a make unique here. And then we need to send a span to that storage we just allocated to the next operation in the chain. We do that right here. Okay, so now we've allocated the storage for the data that we're going to read. So now we need to do that data read. And we do it right here with this async read. And then once that's completed, we just need to make sure that we read the number of bytes that we expected. And then we need to move the buffer when we send it out of here so that whatever function called this async read array will receive that buffer. And that's it. Okay, now we're going to go to an even more complex example once again. So this time, we're going to write a generic, asynchronous, and parallel inclusive scan, which is one of my favorite algorithms. We're going to write it as a pipeable sender adapter so that it can be composed with other sender algorithms. So there's this sender adapter thingy here, which is just sort of a hand-wavy helper struct. So this inclusive scan is going to take 3 parameters. First of all, I'll take a sender, which we will expect to send the input as a range. It will then take an initial value and the number of tiles that it should split the input into. So this is essentially the degree of parallelism that it should use. So we're going to use the classic 2-pass parallel scan approach, which requires some temporary storage for partial results communicated between tiles. We need to allocate this temporary storage asynchronously once the prior sender that's going to send us the input has completed. So we're going to chain a then onto the prior sender. In the body of this continuation, we will just create a vector to hold those partial results. And the first element of that partial results vector we will initialize with that initial value. And we're going to send both the input range and this temporary storage vector to the next sender in the chain. Next, we need to do the first parallel pass, which is called the down sweep. We're going to use the bulk sender adapter here, and that invokes multiple different execution agents in parallel. So the first thing that we need to do for each of the tiles that we're working with is to calculate the range of elements that belong to that tile. So then we're going to take all of the elements in each tile and perform a local serial inclusive scan on them. And we do that right here. So next, we need to propagate information between these different tiles. The sum of each tile needs to be added to the elements of all of the preceding tiles. Now we've already computed that sum. It's the last element of the local inclusive scan of the previous tile. So we store that result into that partials vector, and that's why we have that partials vector there. So assignments to partials from different tiles may happen concurrently because we've spawned them in parallel using bulk, but that's fine because each tile uses a different and unique slot in partials, and no one reads from partials yet, so there's no data races here. Then, after all the tiles have completed their local inclusive scans and written the partials, we need to have one thread do a serial inclusive scan of partials. And we're going to do that here by piping another then sender onto the chain, which will perform the partials inclusive scan. And then this then sender will again just pass along the input sequence and the partials vector. So the result of this scan over partials looks like this. And now as you can see, the information that each tile needs to add to its elements is in the partials slot for the tile directly preceding it. So now we need to go parallel again to distribute that information within all tiles. We call this the upsweep pass. So we'll pipe another bulk, which will once again be over all the tiles. And in the body of the bulk, we'll need to calculate which elements belong to this tile, just as we did before in the downsweep pass. And then we use a serial for each to increment each element in the tile by the appropriate value from the partials vector. So after that addition, we will have the correct result in every element. Finally, we want the sender returned by our asynchronous inclusive scan to only send the input sequence, not the partials vector, because the partials vector is just temporary storage that we allocated and would now like to go away. So we add a final then sender, which only passes along the input. So this means that the partials vector will be destroyed when this then sender completes, because we haven't passed it along, and so its lifetime will just be within the body of this then, and it will be destroyed when this lambda is invoked. And that's it. We are done. We have a generic, asynchronous, and parallel inclusive scan that we can run on any scheduler that we want. Single CPU, CPU thread pool, or a GPU. Okay, so reflection, pattern matching, and senders. I believe that these are the three most exciting C++ features that we are working on, and I think that combined, they will really radically improve how we express ourselves in C++ and allow us to elegantly solve problems that are challenging to solve today. I'd like to thank you all for your time and attention, and I think we've now got plenty of time for questions. And you can come find me afterwards if you want to talk in greater length. You can also check out my other talks on YouTube, including some talks that go into much greater details about how senders work. And I also have a podcast called ADSP with my best friend Connor. And follow me on Twitter and all the other socials. Thank you all.
You had this nice little example about producing JSON.
Yeah.
And you used reflection for that, and you said there are probably some bugs in there. So how do you debugging with reflection?
How do I debug with injection, with reflection?
The reflection. How do you debug your reflection code?
That's a good question. I don't have a good answer for that. It's probably going to be the way that you do any compile time debugging in C++ today, which is that you're going to get some compiler diagnostic. There is no real debugger environment. However, when I said that there were probably bugs in there, the bugs that I was referring to were more like JSON generation bugs, and not so much bugs with how I'm using the reflection facilities. So the bugs are more like output format bugs, things like that. I think that all of the uses of reflection that I showed were fairly simple. Perhaps the one that has the most room for weird issues is actually the traced one, where you're cloning member functions. There's some people who think that that's a bad idea. I know that I've talked with Sean Baxter about this, who writes the Circle compiler, and he believes that it's not a good idea for us to reflect over functions and to do things like generating functions. He'd prefer to just see reflection over data members, because there's a lot of when you're doing things like, I need to clone the protections and the qualifiers and the return type, how exactly does that work, and how does that work if I've got conditional no accept, or a trailing decal type, a trailing return type that has decal type in the thing that I'm cloning. I think that's the example where you're more likely to have quirky things. A lot of compilers are moving to a model for context per evaluation where they have an interpreter instead of just a tree evaluator, where they have like a bytecode interpreter. And I suspect that as we add more metaprogramming facilities, compiler vendors will start to offer some form of interactive interpreter environment where you can do debugging, maybe a compile time debugger. So I think that that's likely something that we're going to need to see more of, especially as we add more and more powerful metaprogramming facilities.
So I would like to continue on this path, because all the generated code from kind of a reflection looked kind of interesting and exciting. But again, it's like you programmed one thing, your application with your metaprogram spit out completely different thing. You don't see that transformation, or is there a way to say, so transform and then emit, so I could look at what is emitted? Does that happen or not really?
So that's an interesting question. When you're doing metaprogramming or code generation with macros, one of the, I'll claim, benefits, because I like macros, is that you can always just run the preprocessor and then look at the preprocessed output and see what's going on. And that's often a good way to figure out what you've done wrong. This is a little bit more complicated because you're sort of doing code generation, but not almost. Can the compiler have a mode where it spits you the post-injected code? Probably. But having a canonical form for what the code looks like, for what the generated C++ source code looks like after injection, may be a bit tricky. But what I mean by that is that there may not be exactly a one-to-one mapping from this injection construct to it expanding to actual C++ code. I'll show you one example of that. Let's just go back to any reflection example. that has a member. So like right here, if in this, that one's actually not a great example. Let's go to the hash append one will illustrate what I mean a little bit better. This right here, this t dot member. So what is this member thing that we're reflecting over right here? Well, it's a data member of this function. So what exactly does splicing it mean? Splicing is supposed to take a reflection and produce a code entity. So does that mean that this thing here produces for you a pointer to the member? That might be what makes sense. There's not really like a code entity that like names the member per se. And by code entity, I mean like something that has like a type, like an object that has a type. Like there's no like way to really think of it otherwise. But we're doing just the dot here. We're not doing dot star. So we're not really applying a pointer to member. And that's the syntax that's used in the proposal for scalable reflection. So it seems to me like this may really just be some special thing. It's sort of hard to think about what exactly this would expand to if you're thinking about like what would this output in terms of like code post injection. Like I think that's one interesting question is like, is this splice here giving me a pointer to a member? Is it giving me some magical construct here? Is it giving me some like new thing that like is a canonical code entity that represents the member? I don't know. So I think we'll probably have some sort of thing that can do that expansion, but I think it's not going to be the case that we'll always have a way to expand back to like C++ source code. All right, other questions?
I'd like to go back to the tracing example on slide 36,
yeah.
If you can. I had a question about if there is some optional things in the list inside the parameter pack. So if you have your list of parameters in the methods that you are doing for tracing, and some of them have default values and some of them don't.
Yeah.
How can you handle this inside this parameter pack thing? Do you have like, in addition to template 4, some sort of template if is that planned or?
Yeah, so the question of like how this works with like default values and like also that, if you need to reflect the default values here too, and that might have some like semantic implications that are troubling. That is, I think, still an open question. Questions like that are, I think, one of the reasons that some people like Sean think that maybe it's not such a good idea to reflect over functions in particular. So I don't have a good answer for you other than, yeah, it's a little bit more complicated than I'm showing here.
More questions? So going forward to the senders,
yeah.
How does that work with coroutines?
How does that work with coroutines? So I think the idea is that an iWaitable would be something that can be treated as a sender. So it can be something that sends a value. So the idea is that they will be able to interop. They are sort of separate constructs, and one is not, replace the other. I think coroutines are generally a much cleaner and nicer way to write asynchronous code because you can write sort of code that appears synchronous but is actually asynchronous, whereas with senders you have to actually sort of write the asynchronous structure. But senders are more powerful. They let you express patterns that you can't as easily express with coroutines, and they let you express task graphs that encompass eager execution in ways that coroutines can't, which makes sender graphs a lot more efficient for certain execution environments. But yeah, the idea is that there will be some interop layer where you'll be able to co-await on a sender, and also where you'd be able to take an awaitable and plug it into a sender pipeline. So there would be some mechanism that would allow you to go in both directions.
So yeah, continuing on the same theme, if you do an await within a sender, does that risk deadlocking your queue, or are the queues like guaranteed to not deadlock in some mechanism?
If you do any sort of blocking within code that's going to run on, the execution agent, you need to be aware of what forward progress guarantees the execution agent gives you. There's a mechanism called a property that all schedulers have that says what forward progress guarantee they provide. If you have an execution agent that doesn't give you concurrent forward progress, you probably should not be blocking, or you need to be very careful in how you do that. But it's not a problem that's going to be exclusive to coroutines.
I have a question too. So can you say what the probability of that these three features land in 26?
So senders is design approved for 26, and I think and we have an implementation and is the most, or there's actually 2 reference implementations. Dietmar's working on one too. That one's the most concrete and the one that I think is most likely to land. It's also the one library feature here, and I run a pretty tight ship, so I feel pretty confident that that one will happen. Reflection, there's a lot more questions there. We spent a bunch of time sort of debating between 2 different designs, and I think we now have clear guidance for which design the committee would like to go with, which was that the last time we looked at this, we wanted to go with the scalable reflection design, which is sort of what I presented today, not per se the TS design. However, there hasn't been a lot of active work on it in the past 1 to 2 years. So if no champion emerges to drive the work, then either the entire effort's going to stall, or some alternative design is going to come around and will make progress because bird in the hand versus 2 in the bush. So that one, I think, has maybe the most questions directionally, even though it's more mature than pattern matching. Pattern matching, there's active work going on. There's at least 2 different groups that are working on proposals in this space. There's, I think, general agreement on a lot of principles. There's some ongoing debate about the specifics of how patterns work. There's this casting model that I didn't present here. This is an as model that may be the direction that we go in. I think that one got some chance for 26, but even though we've had people actively working on it, there hasn't been as many new, recent revisions of the proposal. So we'd really need to see a lot of work in the next year for that to make it into 26. So I would say senders pretty confident for 26. Reflection, I think probably no, unless we really see efforts pick up in the next year. Pattern matching, maybe 50-50. It really depends on what happens in the next year.
Even with these few examples, I think it's critical that the reflection/injection code can get pretty long and complicated, and I imagine parts of them would be reusable in a way that the same pattern will emerge throughout the source code. So to not repeat ourselves, are there proposals also for a way of abstracting parts of it, kind of functions? Template functions are already something different, but make a function that is callable during reflection code within template force, something to organize this bit of mess.
I think that there are some higher level abstractions that we'll want to build around reflection. I think one that's we probably are going to need we'll need some higher level way of doing method cloning, because what I showed was pretty, not amazing. This is not amazing. And if all that you're doing is cloning a method, like cloning all the methods, like there's no need for you to have to repeat this every time. So I suspect we'll probably have some higher level facility for this. I don't know whether it'll be a library function, which I think is possible, or an actual language facility. And I imagine we'll have some other higher level algorithms for doing things like iteration over all the non-static data members. You can imagine some, little library of compile time algorithms for these things. But we already have a lot of these patterns in the sort of the intrinsics, like, the parameters of, parameter types of, et cetera.
With reflection, I can imagine there is great scope for really abusing it and accessing private data members of libraries and stuff like that. So does it imply that there is going to be two levels of accessibility, i.e. things would be marked private, public, private, that sort of, how does that go?
I mean, if you want to abuse protection today, there's already, you have plenty of tools to do, like just pound define private, public. I think that, yeah, there's some potential for abuse here. I think we can probably introduce warnings or diagnostics, or even error out the cases where there's abuses of protection. Maybe we'll require some friend model there. I'm not particularly worried about it because just as with const, it's a protocol that is only valuable if you like honor it. You can abuse it if you want. You maybe shouldn't do that. But if we're too aggressive in doing that, it'll make it hard for us to do useful things like this, like hash append here. This one kind of needs to be able to cheat and to look at your private members. I mean, you could imagine a model where you would need to opt into this, where instead of just having this written like this, like you need to like somehow declare that it's a friend, and then maybe you just have this do, is non-static public data member. But the cost of having to make everybody opt in for that doesn't really seem worth it to me. I mean, yeah, it does introduce a lot of potential for abuse of protection. But I think that a good amount of that potential does exist today.
Sometimes I have data members that should not go into the hash.
Yeah, in which case you'd need to specialize. Like there's nothing that stops you from writing your own overload. This is just like the generic version. Yeah, I mean, like there'll be some cases where this will be wrong if you don't write your own overload. And that is, potentially the danger of something like this.
Yeah, well, my idea was more something like, could I create my own attributes?
Yes, that's actually, I was just thinking as you were saying that. Yeah, so that's one possibility, is that if we had a mechanism for introducing, user-defined attributes, then this hash append function could introduce its own attribute, and you can reflect over attributes. We saw that right here, where I've got the attributes of here. So I think reflection offers a lot of interesting potential for uses of attributes that we hadn't previously, thought of. If you look at other languages like Python does a lot of interesting things with user-defined attributes. We don't currently have a model for defining user attributes, but I think that that's a very valuable thing for us to be looking at. Yeah, that's probably like the correct way to build something like this, is to have some attributes for like opting out certain members. And maybe like the standard library would even need to have like some standard library attributes for just like general purpose, like don't mess around with this member when you're reflecting on things, stuff like that. Like if you, an example of a member that you maybe don't want to like hash, or like having like your printout of something is something that's like a cache, or like a, some scratch space storage that's like the value of it is not really a part of your type.
So I wanted to ask about, we have a talk later about cycle, and I wanted to...
about what?
About cycle, SYCL.
Oh, yes, cycle, yeah.
Cycle, yeah, sorry. So from what I understand, it can accomplish something similar to what senders can do, and so what would be advantages of using senders over that?
Well, the advantage of using senders over Sickle is that senders is something that's on track to be part of the C++ standard, and Sickle is its own thing. I mean, I think it's much better for C++ programmers if we standardize and normalize parallelism and heterogeneous computing in the standard language instead of building our own standards for doing this, because I think people would rather just be able to write standard portable code that runs anywhere instead of having to use things like OpenMP or Sickle